We've done it. We've actually taken a picture of a planet orbiting another star. It's a huge moment, a tiny little pinprick of light, somehow rescued from the overwhelming glare of its sun. But when you really look at the picture, it's just a dot. Is that really the best we can do? After centuries of pointing telescopes at the sky, is our grandest image of another world just a single pixel? What would it take to do better? What would it take to see the continents, oceans, and swirling clouds on a planet in a whole other solar system? To answer not just, is there a planet, but what's that planet like? The answer is a telescope unlike anything ever built before. The answer is a telescope the size of Earth itself. And the wild part, the key ideas that could make it happen are already being tested. Getting there is one of the most ambitious stories in science, and it points to what might be humanity's next great leap. The frustration of a single pixel, that little dot, that one pixel from an exoplanet, is both an incredible victory and incredibly frustrating. For most of the history of finding exoplanets, we didn't even have that. We only knew they existed indirectly. We'd watch for the tiny dip in a star's light as a planet passed in front of it, the transit method. Or we'd measure the slight, rhythmic wobble of a star being tugged on by an invisible planet, a radial velocity method. These are brilliant techniques, and they've shown us that our galaxy is overflowing with thousands of planets. But seeing is believing. And lately, using amazing tools like the James Webb Space Telescope, we've finally started taking actual, direct pictures of these worlds. And still, they're just dots. Sure, we can analyze the light from that dot, breaking it down into a rainbow of colors to hunt for the chemical fingerprints of an atmosphere, things like water, methane, or carbon dioxide. This is how we're looking for biosignatures, the potential signs of life. But it's like trying to understand a forest fire by smelling a faint whiff of smoke from 1,000 miles away. You know something's there, but you can't see the flames, the trees, or what's really going on. So why is this so hard? Why can't we just build a bigger telescope and zoom in? The problem isn't magnification. It's a fundamental limit of light itself called diffraction. Think about dropping a pebble in a pond. The ripples spread out. Light does the exact same thing. As light from a far-off object enters a telescope's lens or hits its mirror, it diffracts, spreading out just a little. This blurs the image. A tiny point of light, like a star, doesn't focus back into a perfect point. It becomes a small, fuzzy disk with faint rings around it. If two things are too close together, like a planet and its star, or two continents on that planet, their fuzzy disks just overlap and blur into one blob. The only way to beat this, to make those fuzzy disks smaller and the picture sharper, is to make the telescopes open way bigger. This has been the story of astronomy for centuries. Galileo's first telescope was just a few centimeters across, but it was just big enough to see Jupiter's moons as separate dots of light. From there, we built bigger and bigger single mirrors, from telescopes you could hold to giants like the 5-meter Halley telescope, then the 10-meter Keck telescopes. The new extremely large telescope will have a main mirror nearly 40 meters across. Every size increase has shown us a new layer of the universe. But to see the surface of a planet like ours, dozens of light years away, to make out features just a few hundred kilometers away, need a telescope hundreds of kilometers across. And for a truly detailed map of an alien world, you'd need a telescope with the effective diameter of an entire planet. Building a solid mirror that big is impossible. It would collapse under its own weight. So, how do you build the impossible? You cheat. How do you build a telescope the size of a planet? The secret to building a planet-sized telescope is, you don't build a planet-sized telescope. At least, not a single, solid one. The secret is a brilliant technique called You actually use this concept every day. Close your eyes, and just listen. You can tell where a sound is coming from, not just because you have one ear, but because you have two. Your brain instinctively processes the tiny, microscopic delay between a sound wave hitting one ear versus the other. It combines those two signals into a single, richer soundscape, giving you a sense of direction. Interferometry does the same thing, but with light and telescopes. Instead of one monster mirror, you use two or more smaller telescopes spread far apart. That distance between them is called the baseline. By combining the light they each collect in a super precise way, you can get the same sharpness, same resolution as a single telescope as wide as that baseline. The power isn't in the size of the mirrors, it's in the distance between them. All of a sudden, the size of your telescope isn't limited by how big you can build a mirror, but by how far apart you can place your telescopes. And this isn't just a theory. We've done it. You've seen the picture. In 2019, We saw something once thought impossible. The shadow of a black hole. That was the work of the Event Horizon Telescope, or EHT. The EHT isn't one observatory. It's a worldwide network of radio telescopes, all linked together. From the deserts of Chile to the mountains of Hawaii, from Spain to the South Pole. These telescopes were synchronized with atomic clocks so accurate they lose only a single second in 100 million years. They all stared at the same spot. The heart of the M87 galaxy, 55 million light-years away. For days, they gathered data not as pictures, but as a flood of radio waves. There was so much information, petabytes of it, that it couldn't be sent over the internet. It had to be flown on hard drives to a central location where supercomputers spent months combining the signals, correcting for the spin of the Earth, our turbulent atmosphere, and the timing of every wave. The result was an absolute triumph. A glowing ring of superheated gas, tracing the edge of the black hole's event horizon, the point of no return. They had used the diameter of the Earth as a virtual lens. The Event Horizon Telescope is a planet-sized telescope. It works. It proved the principle. Now, the challenge is to do it again, but with a much bigger goal in mind. Imaging an exoplanet. The EHT was an incredible proof of concept, but it works with radio waves, which are long and slow. To see an exoplanet in the kind of detail we're dreaming of, oceans, continents, and that's where things get about 1,000,000 times harder. Visible light waves are 1,000,000 times shorter than the radio waves the EHT uses. That means to combine them perfectly, the level of precision you need is 1,000,000 times greater. We're not talking about millimeter accuracy anymore. We're really talking about controlling the positions of telescopes and combining their light with a precision, measured in nanometers, the width of just a few atoms. It's an insane challenge, but it's one scientists are actually working on right now. So let's dream for a second. What does this future telescope look like? First off, it probably isn't on the ground. The same atmosphere that makes stars twinkle is a nightmare for this kind of work. It constantly messes with the light waves, making it almost impossible to combine them perfectly. The real future of a planet-sized telescope is in space. Picture it. A whole fleet of spacecraft, maybe dozens or even hundreds, flying in perfect formation, but together, they act as one enormous virtual mirror. They aren't physically connected, but they're linked by lasers that measure their exact positions down to the nanometer, constantly firing tiny thrusters to keep the whole swarm in formation. This fleet could fly far from Earth, maybe to a quiet spot in space, like the second Lagrange point where JWST hangs out. Once there, it could spread out, its individual telescopes separating over hundreds, or even thousands, of kilometers. So, what would an instrument like that actually see? For the first time, we'd see an Earth-like planet not as a dot, but as a disk, a pale blue dot, maybe, but one with actual features. Over time, as the planet rotates on its axis and orbits its star, we could build a map. We could tell the difference between the blue of oceans and the green, brown, or red of continent. We could watch weather systems form and break apart, and maybe even see the glint of sunlight reflecting off alien clouds. By studying the light from different parts of the planet, we could do more than just guess what it's made of. We could spot the red edge signature that huge forests give off in infrared light. We could see white polar ice caps grow and shrink with the seasons. We wouldn't just be doing astronomy anymore. We'd be doing extraterrestrial geography and meteorology. And the ultimate prize, what if we could look for life, not just by its chemical traces, but by its actions? A telescope this powerful could, theoretically, see the signature of a civilization. On the dark side of a planet, it could potentially pick up the faint, artificial glow of city lights. That would be it. The undeniable proof that we are not alone. The single image that would change everything. The grand engineering challenge. This vision is incredible, but getting from here to there means solving some of the hardest engineering puzzles we've ever faced. Building a planet-sized optical telescope in space isn't one problem. It's 1,000 incredibly complex problems that all have to be solved perfectly. First, there's what we could call the cosmic dance. Precision alignment. Imagine a spacecraft 1,000 kilometers apart. To do this, they have to hold their position relative to each other with a precision of a few nanometers. To put that in perspective, a nanometer is to a meter what 1 second is to 32 years. It's a level of control that's hard to even wrap your head around, especially when these spacecraft are constantly being nudged by solar wind, micrometeoroids, and the gentle push of sunlight itself. Projects like LISA, which will hunt for gravitational waves, are already developing the technologies to make this kind of formation flying possible. Second, you have to block out the star. Exoplanets are ridiculously faint, and their stars are billions of times brighter. Seeing a planet next to its star is like trying to spot a firefly next to a giant searchlight from miles away. The star's glare would wash everything out. The solution could be a separate spacecraft called a star shade, basically a giant, specially shaped screen that flies tens of thousands of kilometers in front of the telescope fleet. It would position itself perfectly to cast a deep shadow over the telescopes, blocking the starlight while letting the faint planet light sneak past its edges. Keeping a star shade and a telescope swarm aligned over those distances is, again, just a mind-bendingly difficult problem. Third, there's the data. The EHT created petabytes of data from just a handful of telescopes. A space-based fleet of hundreds of optical telescopes would produce an absolutely staggering amount of data. All that information has to be time-stamped, sent back to Earth, stored, and then combined. This demands computational power on a scale that would rival the world's biggest supercomputers, all working on one task, turning a hurricane of numbers into a picture of another world. Finally, there's the most down-to-earth challenge: cost and collaboration. A project this big is way beyond what any single country could afford. The James Webb Space Telescope cost about $10 billion and was an international effort. A planet-sized interferometer would be a multi-generational, global project on a scale we've never seen. It would require the political will and commitment of the entire planet, working together for decades toward a single goal. It would be a true species-level project. Beyond exoplanets, rewriting the book on cosmology while seeing another Earth is the goal that really hits you in the gut. A planet-sized telescope wouldn't just be for finding planets. It would be an everything machine that would change every single field of astronomy. With its incredible sharpness, it could look back to the very dawn of time. We could see the first stars switching on in the dark universe, not as faint smudges, but as individual points of light. We could literally watch the first galaxies coming together. It would also be the ultimate black hole observatory. The EHT gave us two amazing portraits of supermassive black holes. This telescope could do the same for thousands of them. We could create movies of matter swirling past the event horizon, testing Einstein's theory of general relativity in ways that are impossible today. Even closer to home, it could see the surfaces of other stars. We could watch star spots and massive flares on distant suns with the same detail we see on our own. We could map the moons and dwarf planets in our outer solar system without ever sending a probe. What it could teach us is almost endless. These amazing ideas fleets of self-guiding spacecraft, giant starshades aren't just scribbles in a sci-fi novel anymore. They are real concepts being developed in labs around the world, the blueprints for the next era of discovery. If you love thinking about huge cosmic projects like this, you might really like our video on building megastructures in space. And as always, subscribing helps us keep exploring these big ideas. The story of astronomy has always been about building bigger eyes. From Galileo's first spyglass to the James Webb Space Telescope, every time we've built a more powerful instrument, our view of the universe has been completely transformed. We are now on the verge of the next transformation. It's a leap that requires us to think beyond a single giant telescope and toward creating a vast, interconnected network, a telescope that isn't one place, but a swarm. The path from the blurry dot we see today to a clear living image of another world is one of the greatest quests of our time. The engineering is staggering, the cost is enormous, and it will take decades. But it's not impossible. It's a challenge worthy of a global civilization, one that asks us to think beyond borders, budgets, and even our own lifetimes. It all comes back to that one fundamental question we ask when we look up at the stars. Are we alone? A planet-sized telescope is the tool that could finally give us the answer. What do you think we'll find when we finally open our planet-sized eye and take a good, long look?